What did we do in the last session? We have started working on what? CNN. Okay. So what are the exercises that you have done on CNN? First thing is, let's see CNN architecture. Let me revise once again. Okay. So I'll just take 5 minutes for brushing up the topics that we have covered earlier. And then we'll start with building CNN model from scratch today in the class. Okay. Now, what is the difference between ANN architecture and CNN architecture? What is the difference between ANN architecture and CNN architecture? How does ANN looks like? The architecture of ANN? We have only input layer, hidden layer and output layers. Whereas in CNN, what do? Before we actually give it to the fully connected layer or the hidden layers or whatever it is, we have two important operations. What are they? Convolution and pooling, not max pooling, pooling in general. It can be max pooling or average pooling. Okay. So what does convolution operation do? What does convolution operation do or helps us in? Extracting the features from the given input image. What does pooling operation do? Reduce the size of the image. Okay, we don't exactly reduce the size of the image, we reduce the dimensions of the image matrix. Okay, so these are the two important operations that we actually perform when we deal with CNN. What are they? Convolution and pooling. Why do we use convolution? For extracting the important features from the image. Use pooling for reducing the dimensions of the image. Once we are done with these two operations, we apply this to fully connected layer. Okay. So in the last two sessions, we were covering on how do we perform convolution operation and how do we do pooling. Okay. So what happens in convolution operation? We apply filters. Okay. We stride the filter over the original image such that the important features would be highlighted, and after I apply filter onto this, only the part of the image which has that features would be having some value. Okay. So convolution operation in this way will help us extract the features. Okay. After that, once I extract the features, I have so many other parameters which are lying beside my important features which I don't want. Hence I apply pooling. Okay. So this is how I extract the features and reduce the dimensions of the image. Okay. Now what you can see here in the image is, I take an input image, apply convolution and then apply activation after the convolution. Why do I apply activation after convolution? Why do I apply activation function after convolution? Because I only want the important features of that particular part of the image to be extracted. As I see, we divide the entire, we have seen koala image, right? We divide the entire image into different parts. First is the upper part or the face, middle part and the lower part of the body, depending upon what image we work on. Okay. So when I'm concentrating on face, in order to identify koala, I want to concentrate much on nose and eyes. So the important features are eyes and nose for me to recognize what that image is all about. Okay. So only these features I want some values and others should be 0. For that we apply activation function which is ReLU. Okay. After that we go for pooling, and once I am done with convolution and pooling, I get a reduced dimension. Now I apply that to the fully connected layer, which is similar to your ANN operation. After fully connected, we give it to the output layer. Okay. Now the one that you see here in the image is only one convolution layer and one pooling layer. Okay. Similar to what we have seen in ANN. What is the advantage of taking more number of hidden layers? More hidden layers we take, more deep understanding of the image happens, such that the accuracy of the model would be increased by identifying the patterns in a clear way. Okay. Similar to ANN with deep layers, we can also take CNN with what? Multiple layers. When I talk about multiple layers, what do I mean? Multiple convolution layers and multiple pooling layers. Okay. So the operation should happen in pairs. One convolution, one pooling. After that, another convolution, another pooling. Not like one convolution, second convolution, third convolution, not like that. So convolution and pooling should happen together. So one convolution, one pooling. After this, another convolution, another pooling. After this, another convolution, another pooling. Okay. If suppose I have an image of large size. Okay, one convolution and one pooling will not reduce the dimension of the image. Hence I go for what? 2 convolution layers or 2 pooling layers. If that is not sufficient, I'll go for third convolution layer and third pooling layer. So this way, depending upon the image we work on, depending upon the data that we take, we either go for one layer or multiple layer. Okay, so this image has only one convolution layer, activation, pooling, fully connected. As you can see in this image, I have one convolution, pooling, second convolution, pooling, fully connected 1, fully connected 2, and then output. Okay, so this way, depending upon the complexity of the data set that we work on, we go for adding more number of convolution layers. Okay, now filters are nothing but what? Feature extractors. We apply these filters during convolution operation. Pooling layer is used to reduce the size of the image dimensions. Okay, now as you can see, this is feature extraction and classification which is done. Now when I talk about first convolution, what am I doing in the first convolution? I am detecting eyes, nose, ears, only one part of the body. In the second convolution layer, I am concentrating on the rest of the part. So depending upon the image complexity, we add so many layers and we concentrate on one part of the image in one layer and proceed with what? Fully connected layer, that is classification operation. Okay, so these are the basic layers that we have seen when we work on what? CNN building. Okay, first is what? Take the input, pre-process that input. We've all done that, right? So when I talk about image pre-processing, what do? We apply padding. What do you mean by padding? It also considers the images at the edges such that the information will not be lost. Okay. After that, we apply what? Convolution layer. So you have done 2 exercises on convolution layer. Taking a matrix, apply convolution. Take a image, apply convolution. Right. After that, we have pooling layer. Okay. So you have done 2 exercises on pooling as well. Take a matrix, apply average pooling or max pooling. Take a image, apply average pooling or max pooling and observe how the dimensions of the images are reduced. Okay. So we are done with 4th step. Okay. So we have seen how do we perform convolution operation. We have seen how do we perform pooling operation. Okay. So today in the class we'll complete the entire CNN building architecture. Okay. So what are the other 2 steps that are remaining? Fully connected layers and the output layer. This is forward propagation. Okay. What do you mean by forward propagation? I take input, I pre-process that input, apply that to convolution layer, apply that to pooling, and then the reduced dimensions would be given to the fully connected layer, and here I go for loss calculation. What is loss calculation again? What is loss calculation? What is loss function? Actual output minus predicted output. What is actual output? What is the predicted output? The difference between this is your loss function. If the loss is more, what do? If the loss is more, that means that the actual output is far different from the predicted output, or the predicted output is far different from actual output. Hence the loss is more, accuracy is less. So I am not satisfied with the output. So what do? I go for back propagation. What do we do in back propagation? What do we do in back propagation? We adjust the weights. Weights here in the sense, the gradients with respect to filters that I applied, the gradients with respect to pooling layers that I have applied. Okay. So today in the class, you will not work on convolution and pooling. We'll put that code as read only. You can just read that. We want you to finish the CNN architecture by focusing on forward propagation and backward propagation. Okay. So when we have discussed about ANN, how do we do forward propagation? First we calculate the transfer function, which is Wx plus B. What is W? Weights into input plus bias term. Apply this to activation function. So we have Z1 and A1. What is Z1? Wx plus B. What is A1? Activation function applied on Z1, right? So we had this calculations when we have done AN. But here how do we do forward propagation? Convolution, pooling, the output of pooling would be given to the loss calculation. So here when I talk about CNN architecture, we have to consider the convolution layer output or the filters and then pooling output. When I talk about backward propagation, how do I adjust my weights here? The weights are nothing but the filter values that I apply or the pooling which I have done. Okay. So today in the class we will be covering forward propagation, backward propagation. Hence we will be done with building CNN architecture. Okay. So as this is our first CNN model, we'll focus only on one layer. Okay. If you have multiple layers, again you'll have difficulty in understanding. So for today the exercise would be on using MNIST dataset. Okay. So what is the dataset that we are working on? MNIST dataset. So that is an image dataset, right? CNN works with images. So in the previous 4 exercises that we have done, we have performed only convolution, only pooling on the matrices and the images. But today we'll take the entire dataset. Okay, we will give you the code for convolution and pooling. What you have to do? Put all the functions of convolution, activation, pooling, and then calculate forward propagation and then define backward propagation. How do you do that? I'll explain. After that we'll proceed with the exercise. Okay. Now this is the architecture of the entire CNN model. Okay. So first I take my image, pre-process that image, apply kernels, that blue. Okay. Now look at this. What is this? My input image, some X image that I have taken. Okay. So what is this, guys? This is the convolution operation that I am doing. So here as you can see, this part is nothing but the filter that I am applying on the entire image. I am dividing this entire image into 9 blocks. Okay. So if you want, you can divide the entire image into some blocks. Okay. And then I apply filter onto each block of the image and I stride and I generate what? The feature map. I generate feature map and on the feature map I apply pooling. Okay. So once I apply pooling, see, I get the convolution feature map. I apply that on the activation function that. After activation function, I'll go for pooling. If required, I'll go for flattening because the output of the pooling will also be 2D only. Yes or no? Will you get pooling in 1 dimension array? The pooling also would be in 2 by 2 array or 3 by 3 array only. So I have to convert that into 1 dimension, for which I apply flattening, and then after I get my flattened 1D array, I give this as input to the fully connected layer. Fully connected layer is nothing but the hidden layers that we usually take for ANN. After that, I take it to the output layer where I apply another activation function which is softmax. So what are the 2 activation functions that we are using, guys? ReLU and softmax. Where do I use ReLU? When I am applying the convolution operation. Why am I using ReLU? Because I want only the important features to be having the value as it is. The rest of them should become 0. The rest of them should become 0. Hence I apply ReLU. Why am I using softmax here? For MNIST data set, I get probability of the value. I want probability saying that this is 2. What is MNIST data set? Handwritten digit recognition where I have digits from 0 to 9. So I want probability prediction saying that this is number 3, this is number 6, this is number 9. So for that probability prediction, what am I taking? Which activation function is the output layer? Softmax. Is it clear? So first I define function for convolution, I define function for activation, I define function for pooling, and you have to use all these 3 functions when you are defining your forward propagation. Is it clear, guys? Is this image clear? So what are the steps to build ANN now, CNN now? First take the image, pre-process the image, apply that to convolution, apply the convolution output to the activation function which is ReLU, apply the activated function to pooling, flatten the image, give that as input to the fully connected, calculate loss. So this will be what? Forward propagation. If the loss is high, we go for backward propagation. Now look at backward propagation. What are we doing in backward propagation here? I will adjust my height, weight, dimensions of the filters and I rearrange them and apply convolution and pooling again and again. Is it clear, everybody? So this is how we work on building ANN. Okay? Yeah. So what is that O11, O12, O21, O22? Can you please tell me? Yes? They are nothing but the feature map that I get after I apply my convolution. Okay. So what is this particular thing? x1, x11, x12, x13, what are these? My original image. Okay, so this is nothing but this part, this blue one. Okay, on which I apply this filter. This filter is represented with what? F11, F12, F21, F22. So when I apply filter onto this original image, I perform element-wise matrix multiplication, and once I am done with that, I will be getting this feature map, which is O11, O12, O21 and O22. So understand that this is my feature map, this is the original image, this is the filter. When I apply filter onto the original image, after matrix multiplication, that is after convolution operation, I will be getting this feature map. Okay. Now once I generate my feature map, so this is how it will be visualized. Okay. So as you can see, x11, x21, but matrix multiplication part. Okay. So how do we calculate it? The gradients. Okay. So forward propagation is easy. We can do that. The original challenge lies in what? Backward propagation. Okay. So we have to calculate the gradients of filter with respect to error E. What did we do for A and N? We calculate the gradients of the loss function with respect to what? With respect to Z1 and A1. What was Z1? The weight matrix. What was A1? The activated matrix. Okay. But here what do? We have to calculate the gradients of the filter with respect to what? The loss function. Okay. Now as you can see here, dou of E by dou F11. What is F11? The filter values that we take. Okay. Dou of E by F12. Dou of E by F21. Dou of E by F22. So in ANN we adjust the weights. Okay. In CNN we adjust what? The filter values. Okay. So we calculate the gradients of the error with respect to what? With respect to filter. Is that clear, everybody? Yes or no? Do you want me to repeat it again? When we talk about ANN, dou of E by dou of Z1, dou of E by dou of A1. Z1 is nothing but Wx plus B. A1 is nothing but activated function of Z1. Okay. But here we calculate dou of E with respect to what? The filter values that we have taken. Okay. Just understand this. Okay. Please feed this into your brains. This is the feature map. This is the original image. This is the filter. So convolution is applied on the original image by applying filter, and we obtain feature map. So if your loss is more, that means that the features are not properly detected. So what do? I can't change my image. My image should be the same. So what do? If my features are not detected properly, I'll calculate the gradients of loss with respect to the filter values and then calculate the feature map again on the same original image. There's no point in changing the image. The image should be the same. I have to change the filter values, apply convolution on that again and calculate the feature map. Is it clear? So this is how we calculate gradients. Okay. So you all okay with this? Yes or no? Now, which evaluates into this, like after solving, okay, after calculating your this thing, it will be evaluated into this, and then finally we will be getting this particular matrix. What is this matrix now? The first back propagation which is done, that is derivatives of the filters with respect to the error function. Okay, so I calculate this and then finally we'll compute the gradients again, go for forward propagation, and then finally we will be getting a required accuracy. Is that clear? So when I talk about backward propagation, what are we doing here? Changing the values of the filters and applying the new filter matrix onto the image and generating a new feature map. Is that clear, everybody? Yes or no? Yes or no? Okay. So this is all about how backpropagation is done in your CNN. Okay. Yeah. So as many times you apply backpropagation, so many times you change the filter, so many times you get the feature map. So if you get the proper feature map, you will be getting low loss function, which indicates good accuracy of the model. So what is step 1? What is step 1? So what are the libraries that I am importing here? NumPy, and I am downloading dataset from what? MNIST from TensorFlow.keras in the datasets. We already have pre-processed dataset which is MNIST. I am taking that from there, and for pre-processing I am using one-hot encoding. Why do we do one-hot encoding? What is the need for, what is label encoding and what is one-hot encoding? Label encoding is just converting the given values into some labels. Okay, 0 is spam, 1 is not spam, like that. When you talk about one-hot encoding for multi-class classification, MNIST I have 10 outputs, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, multi-class. Okay, when I have this multi-class, I don't go for what? Label encoding. Label encoding is used generally for binary. 0 ante yes, 0 ante 1, 0 ante yes, 1 ante no, or 0 ante spam, 1 ante not spam. Okay, but when I have multi-class, I have to go for one-hot encoding. 0 represents 0, 0, 0, 0, 0, 0, 1. 1 represents 0, 0, 0, 0, 0, 0, 0, 1, 0. 2 represents 0, 0, 0, 0, 0, 1, 0, 0. So in this way I have matrix given. Okay. So I am importing 3 libraries, NumPy. Second one is from keras, TensorFlow keras. I am using MNIST dataset, and then from sklearn preprocessing I am importing one-hot encoding. Okay. So second step, I will load the MNIST dataset. Okay. Already in keras we have MNIST dataset. I'll simply load it from there. Okay. I'll perform one-hot encoding on the output labels. See, one-hot encoding should be done on the output labels, not on the input. Okay, label encoding, one-hot encoding for the output variables. For binary output, label encoding. For multi-class, we go for one-hot encoding. Okay, so once I am done with that, I'll go for convolution operation, pooling operation and all that. After that, I'll define my forward propagation. The exercise is open to you all. All the code is in read-only only. Convolution operation pooling, because we've already covered that in the exercises. I don't want you to waste time on doing convolution again, pooling again. Okay, we kept that in read-only mode. Directly switch on to the forward propagation. Okay. Directly switch on to the forward. Look at this. Just give me 2 minutes. So first we add the dimensions for the convolution. We'll define activation functions. Okay. So I've defined ReLU and softmax. Why ReLU and softmax? ReLU for the convolution layer, softmax for the output layer. So in the previous classes we didn't go for backward propagation, hence I didn't calculate the derivatives. But here, as we are going for backward propagation, we also have to calculate the derivatives. Okay. So we calculate ReLU derivative, softmax derivative, and then define the function for convolution operation, which I have already done. Okay, and then we have defined the function for pooling operation. Okay, we have to initialize the parameters here. This is something new for the image matrix, and then we'll go for forward propagation. Is that clear? So directly switch on to step 9. Okay, step 1 to 8 we have already covered in the previous exercises. So I don't want you to waste time and working on the same. Directly switch on to step 9 and start working on forward propagation. Please read the instructions that we have given carefully. Okay. So you are supposed to implement the forward propagation of a convolutional neural network. Okay. So the input that you have taken is a 3D numpy array. Okay. So you have height, width, which are the special dimensions of the image. So you have to return the convoluted output after applying ReLU activation function. Okay. So you have to do convoluted output, pooled output, flattened, prediction, and then loss. Forward propagation should cover all these steps. It's 10:15. We'll give you 20 minutes time for you to complete forward propagation. We have to complete both forward and backward today in the session. We have to build the complete CNN architecture today. 25 minutes for forward, 25 minutes for backward. Please focus on forward propagation now. Okay. Okay, real-time project. So convolution, working on with convolution is very important for you to understand. Okay. So even if you have missed on the other classes, we have kept the code in read only. Please check all 8 steps and then go to 9. If you are already attending regularly, directly carry on with step 9. Understand what we are doing from the beginning. How do we load the data, how convolution is performed, how pooling is done. If you understand that, you can see how forward propagation can be done. Let me quickly give you a glance so that you'll understand and then you can carry on. Okay, look at this. First thing is you have to perform convolution. Okay, so in convolution I already have defined the convol function, right? I am just using that. After that you apply pooling onto the convoluted output. See, conv underscore output is the variable that I am using for convolution operation. On that I apply pooling. After that, for that pooled output I apply flattening, and then using logits function I connect it to my fully connected layer. Okay, and then after I connect it to fully connected layer, I apply it to the loss function. Okay, so these are the 5 steps. First, perform convolution, pooling. See, in the convolution only I am giving it to ReLU. Okay, so convolution along with activation, pooling in the next function, flattening in the third layer, fully connected, and then loss calculation. Okay. 5 steps in forward propagation. Convolution with activation function, pooling, flattening, fully connected, loss calculation. So what is the loss function that we have to use here, guys? This is classification, multi-class classification. So what loss function do we use? Categorical cross entropy. If it is binary, we use binary cross entropy. Okay. See, everything should be in order. You can't do pooling first, convolution next and all that. Convolution, just follow the diagram that we have discussed in the beginning. Convolution plus activation, and then pooling, flattening, fully connected, and then your loss calculation. Okay. Just refer to this image. Let me put that as well. Yeah. Convolution with ReLU, pooling, flattening, fully connected, and then the output layer, the loss calculation. Just follow up this image for forward propagation steps. Apply forward propagation. You take another 5 or 10 minutes, I'm okay, but you have to complete by yourself. They're not giving you the code. There's no test case for forward, but for backward you need forward, right? So there you will go wrong. So that is the reason focus on forward propagation well. There's no test case for this, so you won't get the score, but yeah, after backward propagation you will be evaluating. Another 5 minutes, please complete forward propagation. Let's switch on to backward. Last 5 minutes for you to complete forward propagation. We'll switch on to backward. It takes time. We have test case for backward propagation. So please try to complete forward as soon as possible. Okay. Now we are done with forward propagation. What did we do in forward propagation? First we have done what? In that, what are the parameters that I am passing? And label. Image is nothing but the input, label is nothing but the output. Because when I am predicting my loss function, I want to calculate my output, for which I have to take label. Okay. So there are 5 steps in forward propagation. First is what? I have already defined function for convolution. I am just calling that function, and I am applying that onto the variable called conv_output. So after that I am applying activation function on the convolution. After that I do my pooling, flattening, fully connected, and then loss calculation. Okay. So I have few questions for you when I talk about backward propagation. Okay. Now, did we encounter any errors when we have done backward propagation in ANN? What happens in backward propagation in ANN? Only the weights would be changed. The values of the weights would be changed. So that is the reason we didn't find any error or difficulty in backward propagation. This is your forward propagation. Okay. Okay. So I have few questions for you when I talk about backward propagation. Okay. Now, Did we encounter any errors when we have done backward propagation in ANN? What happens in backward propagation in ANN? Only the weights could be changed. The values of the weights could be changed. So that is the reason we didn't find any error or difficulty in backward propagation for ANNs. Okay, but listen to me very carefully. So my question here is, when I do backward propagation in CNN, I will have problems. We will encounter problems. So what are the problems that we encounter when we do backward propagation in convolution layer in CNN? What are the problems that we face when we do backward propagation in CNN is the question. What do you mean by backward propagation? Output to, loss function to fully connected layer to, let us see the image. So this is the forward pass and backward pass. Forward pass, what did we do? First convolution, activation, pooling, flattening, fully connected, loss calculation. Backward, what do we do? From loss calculation, that is error value to, we go for what? Fully connected layer. Okay. So do we have any problems here when we talk about backward propagation in fully connected? Or during flattening, do we encounter any problems? Or during pooling, do we encounter any problems? Or during convolution, do we encounter any problem? In which step do we encounter the problem and why does that happen? Problem with pooling, okay. Why? Okay, not exactly, but okay. You're not too detailed, it's not correct. Pooling will have problem, one thing. Second problem, flattening. Why? The image is in two dimensional, but flattening is in one dimension. Obviously, there will be a discrepancy because when we are calculating the gradients with respect to filter, we will obviously have problem when we do this 2D to 1D dimension conversion. In ANN, before we apply anything only, we have directly converted 2D into 1D. So we didn't encounter that problem. But here, after processing everything, we are converting 2D into 1D by flattening. So when you go in the reverse way, from 1D you have to convert that into 2D. So here would be one problem. Okay. The problem with pooling is, what does pooling exactly do? Reduce the dimensions of the image. For example, if I have image of 1024 into 1024. So one pooling layer will reduce it to 520 into 520. Second pooling layer may reduce it to 256 into 256 or whatsoever. So from higher to lower it will not be a problem. But in backward propagation, what do we do? First we go for second pooling layer and then first pooling layer. So second pooling layer in the sense the more reduced image. So the bigger image to smaller image reduction will not be a problem. But when we are going for backward propagation, we initially have the lower image, we have to adjust that to higher. Come to the problem when we do backward propagation. One is with flattening, one is with the fully connected layer to flattening, the other one is with the pooling. Okay. So there are three important numpy functions that we use in the backward propagation at each layer. Okay. So we'll see what are those functions. I don't know if you have used it or not, but let me explain you them once. Okay. So the first function here is numpy.outer. Did you use that earlier? Okay. Yeah. So what are the parameters that I am passing here? Numpy.outer basically computes the outer product of two vectors. What does it do? It calculates the outer product of two vectors. That is when you go for matrix multiplication. Okay. Now look at this. The first input layer, input is flattened. The input is flattened, and when you look at this B, the second input, the input is flattened and it is not already minus one dimensional. That is, when you are doing this flattening, 2D to 1D array conversion, I want both of them should be in a similar matrix. For that, we will be using which function, guys? np.outer. Okay. Now, the results would be stored in a variable called OUT, where it will be of normal dimensions for you to process with pooling and all that. Okay. The second function that we use is numpy dot. numpy dot dot function. Did you use this earlier? Okay, why do we use this? For calculating what? The dot product. Okay, okay. If you are okay with this, I am okay. Okay, now look at this. There is another important function called numpy dot zeros underscore like. What is this function? Numpy dot zeros underscore like. So here I told you, right, the dimensions or shape change. What do you mean by dimensions or shape change? For convolution to pooling, when we reduce the dimensions, we have what? One shape for one layer, other shape for other layer. So we have to adjust the size and shape of the pooling layers that we actually use here. Okay. So one layer and mostly we may not get errors. But when you go for one layer, two layer, three pooling, four pooling, you will be obviously getting this error. So we will be using this function. So what does this function do? Let me zoom in. Please read this function. What does this do? Returns an array of zeros. If you have mismatched size and shape of the array from one layer to other layer, we use this function which is called as what? np dot zeros underscore like, which will adjust the shape of the array with same attributes of the returned array. Okay. So returns an array of zeros with the same shape and type of a given array. So I have source and destination, one layer to other layer. If both of them are of different size, we use this function which is called as what? numpy dot zeros underscore like, so that the array adjustments, size, shape would be adjusted. If you don't use this, make error also saying size mismatch, dimensions mismatch, atla errors ostai. Is it clear, everybody? So these are the only three new things that we have to adapt in our code when we go with backward propagation. Is it clear? So what are we doing in backward propagation? See, these are the steps that you have to do in backward propagation. First, read the input image, perform label encoding, convolution operation, activation function on that, pooled operation, flatten, logits, predictions, learning rates. Is it clear? So this is what we'll do. I'll show that in steps. Okay. Nothing, see, if you understand, there's no complication in that. Please try to understand what we are doing. It will be easy. Okay. So what are we doing in step 1? Please make note of these 5 steps. I'll make it easier. Please try to understand it. In step 1, we are trying to calculate the gradients for the fully connected layers. From backward, right? Backward propagation is from fully connected. So here we use this np dot outer because I want to convert that flattened 1D to 2D back. Okay. So first we take logits, that is softmax derivative, which we have already done. On this, I'll apply my np dot outer for the flattened outputs. Is it clear? Now, in step 2, I go for unflattened matching. So I have already applied the outer variable and dot product. I have to convert this 1D vector to 2D back again. So I have to do unflattening. So we do flattening in the forward propagation. In the backward propagation, we do unflattening. Okay. So there's a function called reshape. Okay, already we know that. So by just using that reshape onto this pooled output, we do unflattening. This is step 2. In step 3, we calculate pooling gradients. In step 3, we calculate what? Pooling layer gradients, where we use this np dot zeros alike. Why do we use this function np dot zeros like? To make sure that the dimensions or the shape of the image from one pooling layer or the other pooling layer would match. Okay. So I am using this function. This would be same like your pooling operation or the convolution that you take. Okay. So first perform fully connected layer gradients and then unflatten the image to match it with the pooled output and then calculate the gradients for the pooling layer and then convolution layer gradients and then update the parameters. These are 5 steps. First do fully connected layer gradients. 4 lines. First do that. First complete fully connected. We'll go step by step. Okay. So first complete fully connected layer gradients. First calculate gradients with respect to fully connected layers. We'll go step by step. I know backward propagation is huge, but we'll go with step by step individually. Okay, I'll give you 5 minutes for each step. First, calculate the gradients for fully connected layers. Use np dot outer and dot function here. Calculate the gradients for the fully connected layers. You can just look at a glance if you want. Understand what you're doing. First, try to calculate the gradients for the fully connected layer. See, D underscore logics is nothing but derivatives. I'm trying to take the derivatives, hence I've given those names. D underscore logics. Already we have defined logics. Already we have defined weights by us. Try to define the fully connected layer gradients. What is the point in learning when we give you the entire code? We have clearly given everything in the description. Read that and try working on the code. Calculate fully connected layer gradients. D underscore logics. Pooled output. Calculate fully connected layer gradients and unflatten the image. The output size would be different before you apply flattening and after we apply. Okay. So here we unflatten the image. First calculate the fully connected, unflatten and then apply pooling layer gradients. Practice this code well before you come for the next class. Next class, we will not open any PPT only. Without any PPT, I'll just directly open the exercise and you'll be asked to work on multi-layer CNN. Is that clear, everybody? Why am I using that variable called global? Why am I using that variable called global? I'll ask you this question in the next class. You have to come ready for that. Okay, in NumPy or in Python, why do we use this variable global? Okay, what is the importance of that? First, complete fully connected. After that, unflatten. Once you are done with this, calculate pooling layer gradients as well. What is that for I in range, for j in range in the step 3 convolution pooling layer gradients? The row and column. Okay, I'm trying to adjust the row and column wise. What is that region and max value variables? Region is once I apply one pooling on which particular part. And in those 4 boxes, what is the maximum value? Okay. See, I have a big feature map and I apply pooling on one particular part. That is nothing but the region. In that region, what is the max value? Okay. Again, when I talk about N in range, it is all about pooling height and width. What is the matrix size of the pooling that I am doing? Okay, whether it is 2 by 2, 3 by 3 or whatever you take. First is fully connected gradients, unflatten, pooling layer gradients, convolution layer gradients. All the material here, all the material that I am talking here is will be uploaded onto the Tufan platform. You can download it from there. Okay. So come prepared for the next class reading this particular exercise, because next class also will be doing the same, but on 2-layer convolution and pooling. Okay. Calculate pooling layer and convolution layer gradients. All of you try submitting. Only 7 test cases passed. Only 7 students got their test cases passed. Make it fast. So in the next class you'll be working on another data set, same CNN building from scratch, but not with one pooling and one convolution. You have to work with at least 2 pooling layers and 2 convolution layers. Okay. So along with this, all of you please listen. You'll be having a quiz tomorrow in the next session on Wednesday. Okay. So multiple choice questions would be given. So even they would be considered for your assessment. Okay. So all those who have submitted this can leave. Rest of them please stay back, complete the exercise and then go. Thank you.